Here are solutions to homework set number 9 for ECE 463-663 Modern Control. The first problem is find the shape of a soap film. What a soap film does is it minimizes the surface area. So the problem I have is I've got two rings, one centered at 0, radius of 7. Okay, so that ring kind of spins around. The other one's at 4, radius of 10. Find the shape of that soap film. Well, a soap film minimizes the surface area. This is the functional that minimizes that. So 1 plus y dot squared is length times y gives the surface area. So the circumference is 2 pi r, so there's the 2 pi out in front. Minimize r or y times the length, that'll be the surface area of a soap film. Now from the lecture notes, that's a hyperbolic cosine. To solve, I need to plug in the two endpoints to find a and b. So at the left endpoint, when x equals 0, y is equal to 7. When x equals 4, y is equal to 9. Two equations, two unknowns, solve. Now this is where fmin search comes into play. I'm going to create a function in MATLAB. I'm going to pass my guess of a and b, and if it's correct, these should balance. So bring in the 7 right, bring in the 9 right. These should be equal to 0. That's if I guess right. If I guess wrong, then it's going to be something other than 0. Call it E1, E2. Find a and b to minimize E1, E2. So j is my, do the sum squared error, j will be minimum when E1 and E2 are 0. So setting up that function, and then using fmin search to find it, I'm going to minimize the function soap. Here's my initial guess, and it kicks back saying actually a is 0.6158, b is 1.9224, and here's the sum square difference, basically 0. So that means that here's a and there's b. There's the equation of a soap film connecting those 2 points. And if you plot it, here's what it looks like. So this point is at 7, this point's at 10, and there's the shape of it. If this ever touches 0, the soap film breaks. So that's problem 1. Problem 2. Find the shape of a soap film where the left end point is a ring at radius of 7. The right end point is at 2, and it's like a wetted piece of glass. The soap film will attach to the glass. When I do that, these will be right angles. From calculus variations, I know that the shape of a soap film is a hyperbolic cosine. The endpoint constraints is that the left endpoint, when x is 0, y is 4, and the right endpoint says that fy prime is equal to 0 at the right endpoint. Solving, I get y prime is minus sinh, so this is equal to 0 at the right endpoint, at 2. Two equations, two unknowns, solve for a and b. Again, I'll throw that in MATLAB as a functional. I'm going to guess a and b. Here's the first equation, bringing the 7 right, that should be 0. The second equation should be 0. That's if I guess right. If I guess wrong, these are non-zero. Find a and b to make E1 and E2 0, or find a and b to minimize j, where j is the sum squared difference between the two, or sum squared error. Solving using fmin search, it says that here's a and b. The error is 0, so that's basically the right answer. So there's your soap film. And if you plot the shape of it, here's what it looks like. Left hand points at 7. At 2, this is a right angle. And what it looks like is there's a mirror image going out at 4. Problem 2. Problem 3 is find the shape of a hanging chain. The left end point is 7 meters off the ground. The right end point at 10 meters is 5 meters off the ground. And the length of the chain is 12 meters. It's supposed to be 12. Find the shape of the chain. Oops, is 13 meters. I did that right. So this is what the functional is going to look like. I want to minimize the potential energy. That's this one. Here's the length times height. This is the Lagrange multiplier. The length of the chain is fixed at 13 meters. If I do that, actually going to be this guy, y. There's my functional. Solving that from the lecture notes again, it'll be hyperbolic cosine with the Lagrange multiplier. In addition, the length is fixed, so the integral between 0 and 10 has to be 13. These are the three constraints. So what I'm going to do is set up a function in MATLAB. I'm going to guess A, B, and M. If I guessed correctly, then this equation works at the left endpoint. This equation works at the right endpoint, and the length of the chain is 13. So solving in MATLAB, my initial guess is 1, 2, 3. Fmin search tells me, nope, that's wrong. The actual answer is 3.98, 5.61, 1.64. The sum squared error is basically 0, so that's the correct answer. That tells me here's the shape of the chain. So given A, B, and M, here's the shape. And if I plot it, it goes from 7 at 0, this will slide up, to 5 at 10, and the length is 13. Shape of a hanging chain. Problem 4 looks at solving the find the path to go between 2 points. In this case, I want to go between 6 at x equals 0 to 7 at x equals 10. Find the path that minimizes x squared plus x dot squared. Now, any solution has to satisfy the Euler-Lagrange equation. So taking the partial of f with respect to x gives you 4x. Taking the partial with respect to x dot gives you 10x dot. Now take the full derivative. Any solution has to satisfy this differential equation. I'm using the Laplace operator, where s means derivative. I get 10s squared minus 4 times x equals 0. So either x equals 0, which is the trivial solution, or s is plus or minus 0.6325. Taking the latter solution, I know that x has to follow this path. Plugging in the two endpoints, at 0, x equals 6, at 10, x equals 7. Solve for a and b, and I get a is 0.02, b is 5.97. If I then plot that, here's x of t, here's the optimal path going between 6 and 7 in 10 seconds. This minimizes the cost function. So initially I drive it down. That's where I have the penalty of x squared. Then I come back up. This is penalized with x dot, but overall the cost is minimized. Problem 5 looks at a first-order differential equations. This is leading into optimal control. I want to go between 2 points. X of 0 is 6 at 10 seconds. I want to be at 7. Find the path that minimizes it, subject to the constraint. X satisfies this differential equation, and I want to minimize 2x squared plus 5u squared. Now to do that, I set up my function. Here's my functional, plus a Lagrange multiplier times my constraint. So now I have x, m, and u. The path that satisfies that satisfies 3 Euler-Lagrange equations. Take the partial with respect to x, and I get 4x plus 0.2m. Partial with respect to x dot gives you m. Now take the full derivative. This is the first equation that must be satisfied. Repeat with respect to u. This equation has to be satisfied. Repeat with respect to m, and this equation has to be satisfied. So solve these three differential equations. The way I did that is equation 2 says that m is 2u. Plugging it in, if m is 10u, then that is 10 u dot. Then this bottom equation. Solving for u, I get u is x dot plus 0.2u. Differentiating, u dot is x double prime plus 0.2u x dot. I know that u then over here, I've got this equation substituting. 4x plus 0.2m, and m is 10u. So 0.2 times 2u gives you 2 times u, it's right here, minus m dot, which is minus 10 u dot, which comes in here. Plugging all that in, I have a differential equation in x. Now the x dots cancel, and I wind up with minus 10x double prime plus 4.4x equals 0. Using the Laplace operator, where s means derivative, that's 10s squared minus 10s squared plus 4.4 times x equals 0, saying that s is plus or minus 0.6633. So this is the form of x. Plugging in the two endpoints, at t equals 0, I'm at 6, t equals 10, I'm at 7. Solve for a and b. I get, here's a and b, and here's the optimal path. Okay, so finally, problem 6 and 7 is getting into LQG control. So problem number 6 looks at how do you find feedback gains using LQR techniques. Now we found Kx using pole placement before. This is another way to find Kx. Essentially what you do is you set up the weighting Q and R. And to make it a little bit easier, I made this little script. Here's my A, B, and C matrix. This is the weighting on Y, C transpose C. Here's the weighting on Y dot. So this looks like a spring, that looks like friction. My desired step response is GD. That's going to plot in red. And then find Kx using LQR. These are the two knobs I play with, the weighting on Y and dy. So what I can do is sit there and play with these gains. So the response I want is red. The blue one is the actual response. If I try it with a weighting of 1 and 0, a little bit slow. So let's make this 10 and 0. A little too fast, maybe 9, 6, 4. That's pretty good. So once you find the gains that are right, I can find Kx. And where's MATLAB? Here, MATLAB. There you are. There's Kx and Kr. That's the optimal feedback gain using LQR techniques. And really, it's just same as pole placement. If you take the eigenvalues of the net system, I would get exactly the same answer if I use pole placement, placing the poles here. The advantage of LQR is two of the poles kind of make sense. That tells you the response. The other two aren't really obvious. This is just where the other two poles belong based upon your cost function, keeps the gain small, and keeps the response close. Okay, let's try it again with the ball and beam system. Give it a new A and B matrix, find the optimal feedback gains Kx, well I wouldn't say optimal, find feedback gains Kx to give you this response. I'm going to use the same trick as before. So here is my A and B matrix. My output is position. That tells me Y is just C transpose C. The Q matrix for Y dot is CA transpose CA. Here's my desired response. Find Kx using LQR. If I make the gain 1 and 0, just weight position, I'm pretty darn oscillatory. So let's add some friction to penalize that. Kind of see when I do that, that gets rid of the oscillations. And just kind of playing with the gains, trying to get it close. Okay, that was too much. Let's increase the gain on position. And it's kind of hard getting there. Another approach, let's copy paste, is to treat these just as gains. So we're going to have Q being diagonal of 1, 0, 0, 0. Play with those 4 knobs. So let's increase the weighting on X dot. That got rid of the oscillations. And let's see what happens when I change this number. Increase the weighting on Q, on theta I mean, the second state. And not a huge impact. Well, not too bad. Well, that's pretty good. So these are just knobs to play with. Once you're done, I can find the feedback gains. So here's Kx. Come on, puppy dog. Here's Kx, the feedback gains. Here's Kr. And the optimal place to put the poles. But what I had, these two kind of make sense. That tells you the settling time. These two are kind of odd. It's wherever they go based upon my cost function. So again, LQR is sort of like pole placement, except I've got 2 knobs to play with, maybe 4 knobs. Play with the knobs until the response is right. Just another way to find the gains. Here I actually had higher gains than pole placement, which makes you think that maybe this is actually worse than pole placement. One oddity, though, is that I can actually get a better response than I want without using very big gains. For example, the red line is my desired response. Let's get rid of those oscillations. That's not too bad. This is actually faster than I want. It's actually easier to make the system faster than my desired response. It takes control effort to slow it down. Probably a better way to do this is design a faster system, and then rather than having a step input, I would have the input be like a ramp to slow it down. If I did that, I'd have a smaller gains, gives you smaller gains, or smaller Kx. Come back. There, the Kx is much more reasonable. And it says, rather than putting the poles at minus 0.5 for 8-second settling time, it's actually easier moving them over to minus 0.9. And where that kind of comes from is my open loop poles at plus 2.72. It's actually easier moving this to minus 2.72 than it is to move it somewhere else. And these 2 complex poles apparently got moved over here. But anyway, LQR is just another way to find your feedback gain Kx. It's a tool. Pretty much if the tool works for you, use it. If it doesn't work, don't use it. Except if it's a homework set where I'm telling you to use this tool, then you kind of have to use it. But in industry, when you get there, pole placement is a way to find the feedback gains. LQR is a way to find the feedback gains. It's just a useful tool. Some people like pole placement. Some people like optimal control LQR techniques. But anyway, that is homework set number 9 for 463 Modern Control.